We're now going to discuss how the gradient vector can be used to find the tangent line to a level curve and as well the tangent plane to a level surface. As a reminder, a level curve can be interpreted as the projection of the horizontal trace curves or the intersection curves when I slice a surface with a horizontal plane, and then we get that trace curve shadow projected down into the floor. So that is a level curve. As we've discussed before, the gradient vector points the way to the path of steepest descent. And the gradient vector is a two-dimensional vector in the floor. So if we were to come down to being a point on this level curve, the gradient vector is going to point into the direction of the path of steepest descent. And what we'll find is that that gradient vector is also a perpendicular vector to the line that is tangent to the level curve at that point. So just to reiterate, the gradient vector del f is perpendicular to the tangent line of a level curve in two-dimensional space. So let's look at this image of level curves. If we were to pick any point on one of these level curves, let's say this point out here, the gradient vector is going to be pointing in the path of steepest descent. To determine what direction that would be, we can think about where the tangent line would be at this point, and the gradient vector is going to be pointing perpendicular to the tangent line. So if we were standing on our surface at this point, we would need to travel in this direction to achieve the path of steepest descent. Now, this concept can be flown up a dimension. Instead of a 3D surface with two-dimensional level curves, now let's look at a 4D, I'm going to call this a blob because it's not something that we can graph, that has three-dimensional level surfaces. Similarly, the gradient vector is one dimension lower than the surface itself, just like back here in 3D. If we have a 3D surface, our gradient vector is a two-dimensional vector in the floor. So here, if we have a four-dimensional blob, then the gradient vector is a three-dimensional vector in R3. And what we'll see here is that this gradient vector is perpendicular to not a tangent line, but in a higher dimension, this would be the tangent plane. So our higher dimension interpretation of the gradient vector is that it's perpendicular to a tangent plane in 3 dimensions in this scenario, where we were perpendicular to a tangent line in lower dimensions. Now this is quite helpful because we know that in order to get the equation of a tangent plane, what we need are, number one, any point in the plane, but number two, a normal vector or a vector that's perpendicular to that plane. And what we'll see here is that we can use this gradient vector as our normal vector to help us get the equation of a plane that's tangent to a surface. Well, here we have a three-dimensional surface, but this scenario of using that gradient vector is only going to work if this 3D surface is a level surface of some four-dimensional, I'm not going to call it a surface, I'm going to call it a blob. So because we're wanting to find the equation of the tangent plane and we want to use that gradient vector as our normal vector, we need to consider this as a three-dimensional level surface of some four-dimensional blob. So how do we do that? It's actually not too bad. What we're going to do is set this equal to 0 by subtracting x from both sides. So we'll have y squared plus z squared minus x minus 2 is equal to 0. We can say that all the terms on the left-hand side make up that four-dimensional function, and our original surface is the level surface for this four-dimensional equation when the altitude or the output or the range element is equal to 0. So our level surface is when w is equal to 0, and then we might have another level surface out here when w is equal to 1, and so on. So we're going to let our 4D function be equal to y squared plus z squared minus x minus 2, and we want to find the gradient of this four-dimensional function because that gradient of the 4D function is a 3D vector that's perpendicular to the tangent plane, and that's the tangent plane that we're after. So the formula for finding this three-dimensional gradient vector is basically the same as it was for the lower dimensions. We're looking at the first partial of f with respect to x, the first partial of f with respect to y, the first partial of f with respect to z is now being added in so that we get this three-dimensional gradient vector. So our first partial with respect to x is going to hold y and z constant, and the derivative of negative x is just going to be negative 1. The first partial with respect to y is going to hold x and z constant, and the derivative of y squared then is just 2y. The first partial with respect to z holds x and y constant, which is going to give us the derivative of z squared, which is 2z. So our gradient vector function, depending on the x, y, z ordered triple, is going to be -1 is the first partial with respect to x, 2y was the first partial with respect to y, and 2z was the first partial with respect to z. Now remember, to get the equation of any plane, we need two things. We need a point, and we need a normal vector, and we're going to use this three-dimensional gradient vector because the gradient is perpendicular to the tangent plane that we're after. But we need this specific gradient vector, meaning we need to figure out what this gradient is at our point of interest. So back up here to the problem, we see that we were interested in the point -1, 1, 0, so that's our point. And in order to get this specific gradient vector, we see that the x component of the gradient vector is a constant -1. The y component of the gradient vector depends on the y coordinate of the point, which is 1. It's 2 times y, or 2 times 1, which is 2. The z component of the gradient vector depends on the z coordinate of the point. 2 times 0 is 0. So let's also recall that one of the ways that we go about finding a plane that passes through some given point, x naught, y naught, z naught, and has a normal vector that is ABC. The formula for the plane equation was a times x minus x naught plus b times y minus y naught plus c times z minus z naught. And all of that adds together to be 0. So using our point and our normal vector, which is the gradient vector, we'll say the x component of the gradient vector, -1, times x minus the x coordinate of the point, which is -1, so minus a -1 is +1, plus the y component of our normal vector or gradient vector times y minus the y coordinate of our point, which is 1, plus the z coordinate of our normal vector times z minus z naught, which is 0. And all of this adds to 0. So now we simplify. We have -x minus 1 plus 2y minus 2, and all of this is 0, so we add up to 0. And then we'll just rearrange the terms. -x plus 2y minus 3 equals 0, and this is the equation of the plane that is tangent to our surface at the given point. So let's look at all of this in 3D graphing software to interpret our findings. So this is the 3D graphing software that comes stock on a MacBook Pro, and I've entered in our surface function here, the original equation that was given. It is a circular paraboloid that is surrounding the x-axis, or opening in the direction of x. So here I am looking at the first octant. This is the positive y-axis, positive z-axis, and positive x-axis is in the center of the circular paraboloid. The ordered triple in question is -1, 1, 0, so I've got that point kind of back here on the surface. We found our gradient vector to be this vector that is extending out of that point, and our tangent plane equation that we found using the gradient vector as the normal vector was -x plus 2y minus 3 is equal to 0, and we can see that that plane is tangent to our surface at that ordered triple, and that gradient vector does appear to be perpendicular to it. So since everything is lining up, I'm feeling pretty good about our answer.